So this is number 3 in your third exam review, where it says that when Mendel conducted his famous genetics experiment with peas, one sample of offspring consisted of 428 green peas and 152 yellow peas. So you can see that the total number of peas that were sampled was equal to 580. In A, you're asked to determine a 96% confidence interval estimate of the percentage of yellow peas. And you've learned a formula for calculating a confidence interval for a proportion. And I may be using slightly different variables. You take your sample proportion P hat plus or minus your Z, I call it Z star. I see your professor calls it Z of alpha over 2, means the same thing, times the standard error of your proportion, which is the square root of your P hat times your Q hat divided by N. So that's your basic formula for a confidence interval for a proportion. And in A, he's wanting you to construct a confidence interval for a proportion of yellow peas. So to get your P hat for yellow, you need to take the number of yellows that were in your sample, 428, and divide by the total number of peas. And if we take 428 divided by 580, we get a sample proportion of about 0.7379. Okay? Now, I see why you're a bit confused by your professor's work because he has his P hat and Q hat labeled backwards. Let me take a look at why. Yeah, he did make a mistake. I think he is using the proportion of green peas instead of the proportion of yellow peas. So I disagree with his answer as well. So our proportion of yellow peas, our P hat is 0.7379. So that's going to be our what we call our point estimate. Our Z star is, I agree with the 2.05. What you have to do is cut the left out percentage. You've got 96% confidence interval, so you've left out 4%, but you have to split that 4% in half because in a confidence interval, you're capturing the middle percentage of your normal curve. And that means the remaining 4% that's not in the middle, half of it needs to go in this upper tail, and half of it needs to go in this lower tail. So to find what we call your upper critical value for your confidence interval, this value right here, we have to consider the fact that there's a total of 98% that is below it because there's only 2% that is above it. So what you have to do, I believe this is probably how you've been taught to do it. You go to that table of standard normal probabilities and you have to look in the body of that table and try to find a number as close to 0.9800 as you can get. And you can see that the closest you can get is 0.9798. And that corresponds to a z-score of 2.05. So that's where this critical value of 2.05 comes from. If you need me to further clarify that, don't hesitate to send me a message. But then moving on to our standard error, we need to multiply that critical value by the square root of our P hat, which is 0.7379, times our Q hat, which we know is 1 minus 0.7379, 0.2621, and divide that by N, and in our case, N is 580. So now if I calculate the part of the confidence interval that comes after the plus or minus, which we typically call the margin of error, I get a margin of error of 0.0374. I typed it in just as is, 2.05 times square root, and then 0.7379 times 0.2621 divided by 580 equals. And I got that margin of error. So to get the lower boundary of our confidence interval, we have to take our p-hat of 0.7379 and subtract 0.0374. And our lower boundary would therefore be 0.7005. To get the upper end of this confidence interval, we have to add that margin of error to our 0.7379, and that would be 0.7753. So we basically can say that we're 96% certain that the true percentage of yellow peas in the population of all peas is somewhere between 70.05% and 77.53%. Okay, so now I'm looking at my work, and I now see that, no, I'm the one that goofed, not your professor. There were 152 yellow peas, not 428. I used the green. Must be too early in the morning. So our p-hat is 0.2621. Our margin of error isn't going to change, but our p-hat is going to change. And therefore, the lower end of our boundary of our confidence interval found by taking the 0.2621 minus our margin of error is 0.2247. And the upper boundary, when we do plus our margin of error, is 0.2995. So I do agree. I apologize, Jordan. So we're 96% certain that the population of all yellow peas is somewhere between 22.47% and 29.95%. So then in B it says, based on his theory of genetics, Mendel expected that 25% of the offspring would be yellow. Given that the percentage of offspring yellow peas is not 25%, do the results contradict Mendel's theory? Well, notice when you look at this interval, 25% is somewhere pretty close to the very center of it. In fact, it's somewhere in between the lower end and the upper end of the confidence interval. And we said that we're 96% certain that the true percentage of yellow peas is in that interval. Now we see that what he claims is the true percentage, 25%, does fall in that interval. Therefore, we don't have evidence against that claim. We actually have evidence that supports that claim. So once again, I hope that helps, Jordan. And again, I'll be around all morning. So if you have other questions when you're up and about and take a look at these videos, please do not hesitate to message me.